For the processor. In our previous lectures, we complete the simple data path, and now we can add the control unit with that simple data path. The control unit must be able to take inputs and generate a write signal for each state element. The selector control for each multiplexer and the ALU control. The ALU control is different in number of ways, and it will be useful to design it first before we design the rest of the control unit. So for simple implementation scheme, we look at what might be thought of a simple implementation of our LEGV8 subset. We built this simple implementation using the data path of the last section and adding a simple control function. This simple implementation covers load register LDUR, store register STUR, compare and branch 0 CBZ, and the arithmetic logical instructions add, sub, and or. Then we will later enhance the design to include an unconditional branch instruction B. The LEGV8 ALU defines the 6 following combination of 4 control inputs: 0000, 0001, 0010, 0110, 0111, and last one is 1100. We see that ALU control lines, when all these control lines are 0000, it performs functions of AND operation. When control lines are 0001, it performs function OR. When control lines are 0010, add function is performed. 0110, then subtract function is performed by the ALU, and when the control lines are 0111, pass input B function is performed by the ALU, and in the last, when the control lines are 1100, then NOR function performed by the ALU. So depending on the instruction class, the ALU will need to perform one of these first 5 functions. Because NOR can be used for other parts of LEGV8 instruction set not found in the subset we are implementing. So for load register and store register instructions, we use the ALU to compute the memory address by addition. For the R type instruction, the ALU needs to perform one of the 4 actions: AND, OR, subtract, or add, and depending on the value of 1 bit opcode field in the instructions we read in chapter 2. So for compare and branch 0, the ALU just pass the register input value. We can generate the 4-bit ALU control input using a small control unit that has inputs the opcode field of the instruction and a 2-bit control field which we call ALU OP. ALU operation indicates whether the operation to be performed should be add, mean 00 for load and store, pass input B 01 for CBZ instructions, are be determined by the operation enclosed in the opcode field 10. Similarly, the output of the ALU control unit is a 4-bit signal that directly controls the ALU by generating one of the 4-bit combinations which are 0 0 0 0 0 0 0 1 0 0 1 0 0 1 1 0 0 1 1 1 and last one is 1 1 0 0. The ALU control inputs based on the 2-bit ALU operation controlled and the 11-bit opcode. This style of using multiple levels of decoding, that is, the main control unit generates the ALU OP bits which then are used as input to the ALU control that generates the actual signals to control the ALU unit. It is a common implementation technique. Using multiple level of control can reduce the size of the main control unit. Using several smaller control units may also potentially reduce the latency of the control unit. Such optimizations are important since the latency of the control unit is often a critical factor in determining the clock cycle time. There are several different ways to implement the mapping from the 2-bit ALU OP field and the 11-bit opcode field to the 4 ALU operation control bits. Because only a small number of the 2048 possible values of the opcode field are of interest and the opcode field is used only when the ALU operation bits equal to 10, we can use a small piece of logic that recognizes the subset of possible values and generates the appropriate ALU control signal. In this figure, the ALU control bits are set depends on the ALU OP control bits and the different opcodes for the R-type instructions. The instructions listed in the first column determine the setting of the ALU OP bits so that when the ALU operation code is 00 or 01, the desired ALU action does not depend on the opcode field. In this case, we say that we don't care about the value of the opcode and the bits are shown as X. When the ALU OP value is 10, then the opcode is used to set the ALU control inputs. As a step in designing this logic, it is useful to create a truth table for the interesting combinations of the opcode field and the ALU operation signals. This truth table shows how the 4-bit ALU control is set depending on these two input fields. Since the truth table is very large, approximately 8192 entries, and we do not care about the values of the ALU control for many of these input combinations. So only the truth table entries for which the ALU control must have a specific value we are interested. Because in many instances we do not care about the values of some of the inputs, and because we wish to keep the table compact, we also indicate don't care term. A don't care term in this truth table represented by an X in an input column indicates that the output does not depend on the value of input corresponding to this column. For example, when the ALU OP bits are 00, as in the first row of this figure, we always set the ALU control to 0010, independent of the opcode. In this case, then the opcode inputs will be don't care in this line of the truth table. Later we will see some examples of another type of don't care terms. Once the truth table has been constructed, it can be optimized and then turned into gates. This process is completely mechanical, so rather than show the final steps here, we describe the process and the results. For more detail, you may see the Appendix C of your textbooks. Now that we have described how to design an ALU that uses the opcode and a 2-bit signal as its control inputs, now we can return to looking at the rest of the control unit. To start this process, let's identify the fields of an instruction and the control lines that are needed for the data path we constructed in previous lecture to understand how to connect the fields of an instruction to the data path. So it is useful to review the formats. The three instruction classes are R-type, load and store, and the conditional branch. Use three different instruction format. First one is instruction format for R format instructions. In these instructions we have three registers operands Rn, Rm and Rd. Fields Rn and Rm are sources and Rd is the destination. The ALU function in the opcode field and is decoded by the ALU control design in previous lecture. The R-type instruction that we implement are add, sub, and or. The shift amount field SHAMT field is used only for shifts. We will ignore it in this section. Second one instruction format is load. The instruction format for load and store instructions. The register Rn is the base register that is added to the 9-bit address field to form the memory addresses. For load, RT is the destination register for the load values, and for store, RT is the source register whose value should be stored into memory. The last instruction set is instruction format for compare and branch on 0. The register RT is the source register that is tested for 0. The 19-bit address field is sign extended, shifted and added to the PC mean program counter to compute the branch target address. So there are several major observations about these instruction format. Number one, the opcode field is between 6 and 11 bits wide and found in bits 26 to 31 or between bits 21 to 31. The Second point is the first register operand is always in bit position 5 to 9. Rn for both R-type instructions and for the base register for load and store instructions. Number third, the other register operands is in one of two places. It is in bit position 16 to 20, which is RM for R-type instructions, and it is in bit position 0 to 4 for RT for the register to be written by load instruction. That is also the field that specifies the register to tested for 0 for compare and branch instructions on 0. So we will need to add a multiplexer to select which field of the instruction is used to indicate the register number to be read. Next point is another operand can also be a 19-bit offset for compare and branch on 0 or a 9-bit offset for load and store instructions. The last one is the destination register for R-type instruction RD, and for load RT is in bit position 0 to 4. So the first design principle, simplicity favors regularity, we learn in chapter 2, pays off here in specific control. Now using this information, we can add the instruction labels and extra multiplexer to the simple data path we learned in previous lectures. The control lines are shown in colors. The ALU control block has also been added. The write signal for state elements, the read signal for the data memory, and the control signal for the multiplexers are also added. Since all the multiplexers have two inputs, they each require a single control line. This figure shows even single bit control lines plus the 2-bit ALU operation control signals. We have already defined how the ALU OP control signal works, and it is useful to define what the 7 other control signals do informally before we determine how to set these control signals during instruction execution. Now that we have looked at the function of each of the control signal, we can look at how to set them. The control unit can set all but one of the control signals based solely on the opcode field of the instructions. So in the first column you may see the signal name, which are REG to LOC, mean register to location. Second one, REG write, mean register write. ALUS RC PC SRC MEMRED memory read, memory write, and memory to register. The effect of each of the 7 control signals, REG to LOC, when the register number for read register 2 comes from the RM field, means from bit 16 to 20, the signal is deserted. And when the register number for read register 2 comes from the RT field 0 to 4, this signal is asserted. Similarly, reg write, it has no deserted action. As a asserted action, the register on the write register input is written when the value of the write data input. ALU SRC, the second ALU operand, comes from the second register field output, and when ALUSRC is asserted, the second ALU operand is the sign extended lower 16 bit of the instruction. When the PC is replaced by the output of the address that computes the value of PC plus 4, then PCSRC is deserted, and when the PC is replaced by the output of the adder that computes the branch target, then PCSRC is asserted. Memory read has no deserted action, but when data memory contents designate by the address input are put on the read data output, then memory read signal is asserted. Similarly, memory write has no deserted action, and for asserted action is taken when data memory contents designated by the address input are replaced by the value on the write data input. In the last, the value of fed to the register write data input comes from the ALU, then memory to register is deserted. And when the value fed to the register write data input comes from the data memory, then memory to register signal is asserted. The PCSRC control lines is the exception. That control line should be asserted if the instruction is compared and branch on 0, and the 0 output of the ALU, which is used for the 0 test, is asserted to generate the PCSRC signal. We will need to AND together a signal from the control unit, which we call branch, with the 0 signal out of the ALU. These 9 signals can now be set based on the input signal to the control unit, which are the opcode bits from 21 to 31. So this figure shows the data path with the control unit and the control signals. Now, before try to write a set of equations or a truth table for the control unit, it will be useful to try to define the control function informally, because the setting of the control lines depends only on the opcode. So each control signal should be 0, 1 or don't care for each of the opcode values. This simple data path and the control unit figure, the input to the control unit is the 11-bit opcode field from the instruction. The output of the control unit consists of 3 1-bit signals that are used to control multiplexers are REG to LOC, ALU, SRC, and MEM to REG. Similarly, 3 signals for controlling read and write in the register file and data memories are REG write, MEM read and MEM write. Also a 1-bit signal used in determining whether to possibly branch, and a 2-bit control signal for the ALU operation, and an AND gate is used to combine the branch control signal and the zero output from the ALU. The AND gate output controls the selection of the next PC. Notice that PC SRC is now a derived signal rather than one coming directly from the control unit. This table defines how the control signal should be set for each opcode. This information follows from the previous figure, which is simple data path with the control unit. The first row of the table corresponds to the R format instructions, which are add, subtract, and OR instructions. For all these instructions, the source register fields are RN and RM, and the destination register field is RD. This defines how the signal ALU, SRC, and REG to LOC are set. Furthermore, an R-type instruction writes a register REG write is equal to 1, but neither reads nor writes data memory. When the branch control signal is 0, the PC is unconditionally replaced with PC plus 4. Otherwise, the PC is replaced by the branch target if the 0 output of the ALU is also high. The ALU OP field for R-type instructions is set to 10 to indicate that the ALU control should be generated from the opcode field. The second and third row of this table gives the control signal setting for load and store instructions. These ALU, SRC, and ALU OP fields are set to perform the address calculation. The memory read and memory write are set to perform the memory access. Finally, REG to LOC and REG write are set for a load to cause the result to be stored in the RD register. The ALU OP field for branch is set for a pass input B, which means ALU control is equal to 0, 1, which is used to test for 0. So notice that the memory to REG field is irrelevant when the REG write signal is 0. Since the register is not being written, the value of the data on the register data write port is not used. So the entry memory to REG is the last two rows of the table is replaced with X, means don't care. A don't care can also be added to REG to LOC for load instruction, which does not use a second register. This type of don't care must be added by the designer since it depends on knowledge of how the data path works.